This is part 2 of section 9.1 Similarity. We just finished with example 5 in part 1. This is the last example in the lesson and an extra example reviewing factoring quadratic equations as a method to solving quadratic equations from Algebra 1. So 2 more examples. Example 6, rock climbing. Before rock climbing, Darius wants to know how high he will climb. So he starts at the cliff, and he starts moving back some sort of distance. He moved back 34 feet, a nice good distance. He sets a mirror down on the ground where the mirror's facing up, and he comes back further until he can see the reflection of the top of the cliff through the mirror here. So his head is right up here at point H. As soon as he can see the reflection of the cliff in the mirror, J up here, he stops. That's 6 feet away from where he put the mirror. So he's already got TV and he's got SV, these two distances, 34 feet and 6 feet. He knows that he's 5.5 feet high or tall, and we're wanting to know, or the problem asks for how tall that cliff is. So he can find the length or height of that cliff without having to physically measure it because it's too high. So to start off, this is a similarity problem. We've got what looks like two right triangles. Can we assume these are right angles? Yes, because we assume Darius is standing straight and we assume the cliff starts at a right angle. So we've already got these two angles are congruent because of right angles congruence theorem. So we have angle T is congruent to angle S by right angle congruence theorem. And so there's one pair of angles that are congruent. Now remember, we can either try to use AA similarity, SAS similarity, or SSS similarity. We've already got one pair of angles, so SSS is probably out. And if you'll take a close look at your diagram, we know that angle HVT is congruent, given to us, is congruent to angle JVS. There's a reason why these are congruent, and you'll get to that. We'll get to that later, but these two are given congruent to us, the reflection on both directions. So that's given. So that's two angles, two pairs of angles in two triangles. That's all we need. So by the AA Similarity Postulate for similarity, we can now declare that these two triangles are similar. Well, if they're similar, all their corresponding sides must be proportional. So since we're looking for the height of the cliff, which is JS, or X, we'll get to that in a moment, JS corresponds with his height, HT. And then the two sides we do have are these bottom sides of both triangles, the distances he walked out. So back to the larger triangle, from the base of the cliff to the mirror is 34 feet, and that was VS, is to the length back from the mirror to where he's standing, VT. So substituting in those values, JS, we get X over HT, which is 5.5 is height, equals VS, which he measured off 34 feet, to VT, which he measured back from the mirror 6 feet. Now, because we have a proportion, we can use cross products or cross multiply, and when we do that, we get 6x equals 187. Dividing both sides by 6, we get x, and then we don't get an exact value. We're going to approximate and round to the nearest whole number, or nearest foot. That's the ones place. So when we do that, dividing 187 by 6, we get about 31 feet. So the cliff is about 31 feet tall, and he didn't even have to climb the cliff to do it. Finally, this is an extra example. You're going to experience having to go back and use factoring as a method, you're going to end up with a quadratic equation sometimes in some of these problems when you cross multiply with proportions. So let's take an example. In the diagram, triangle ABC is similar to triangle EDC. So ABC is similar to triangle EDC. Find the value or values of x, then find the length of BC. This one right here. Well, first of all, define x. Since we already know these two triangles are similar, all their corresponding sides are proportional. So I'm going to take AB in the larger one is to ED in the smaller one as, and I'm going to come over here back over to the larger triangle, BC in the larger one is to DC in the smaller one. Substituting in those values, since we know they're similar, we have 5 is to ED, which is x, as BC, which is 2x minus 7, is to DC, which is 3. Since we have two ratios set equal to each other, we can cross multiply now. We can cross multiply this way. We get x times 2x minus 7 equals 5 times 3. Then further multiplying using the distributive property here, x times 2x is 2x squared. X times minus 7 is minus 7x equals 5 times 3 is 15. Now, because we have an x or a variable squared, this is a quadratic equation. It's not a linear equation. And there's only a few methods you've learned how to use to solve an equation like this. One of those methods is factoring. But regardless of the method, we need to, when you have an x squared or a y squared or whatever variable squared, you've got to get everything else over to one side. And if you'll remember, the quadratic form is ax squared plus bx plus c equals 0. Everything must be set equal to 0 in descending order. So I subtract 15 from both sides, and I get 2x squared minus 7x minus 15 equals 0. I did that on purpose. Now, there's a law in algebra that says anytime you multiply two numbers together and you get 0, either A has to be 0, the first factor, or B has to be 0, the second factor, or both. So using that property, we can hopefully factor this into two factors and set it equal to 0, both of them equal to 0. Let's try and see if we can factor that. Remember, a trinomial in this form usually factors into two binomials. Set it equal to 0. Don't forget that. 2x squared factors into 2x and x. So I'll put 2x here in the first place, and in the first place over here, x. Then I come over to the last term and notice that 15, leaving out the negative for right now, 15 has factors of 15 times 1. Also has factors of 3 times 5. It's up to us to figure out which pair of these fit here and here so that when we multiply the outer terms and the inner terms, we get negative 7x. If I try 3 times 5, let's say I put 5 here and 3 here. 2x times 3 is 6x. 5 times x is 5x. Well, you try to add 6x and 5x or subtract them, and there's no way you can get a 7 or negative 7. So 5 and 3 in this order will not work. So we switch the order and put 3 here and 5 here. See if this works. 2x times 5 is 10x. 3 times x is 3x. And lo and behold, if we subtract 3 from 10, we do get 7. Only if 10 is negative. So negative 10x plus 3x gives us negative 7x. So this is the combination that works. And the 10x has to be negative. So the product of 2x times 5 must be negative or minus. And 3x must be plus or positive. Now that we've factored it into two factors, we use this property here. And we can now say that either 2x, one of the factors, plus 3 equals 0, or the other factor, x minus 5 equals 0. We solve for both equations. In the first equation, we subtract 3 from both sides and get 2x equal negative 3. And then dividing both sides by 2, we get x equal negative 3 halves. In this equation, we add 5 to both sides, and x is equal to 5. Now, before we immediately declare that this one won't work, we need to make sure that it really doesn't work because it's negative. Remember, length or distance cannot be negative. If we put it in here, we're still going to get a negative here, but be careful when you plug it in. Because this is x, only x, and it's a length, then it cannot be negative. So negative 3 halves or negative 1.5 will not work. However, over here, x equal 5 will work because it is positive. So the value of x should be 5 for these two triangles to be similar.